So this last lecture in this series of 12 deals with the design of a bulk nanostructured steel. And I'll explain what that actually means in the next slide. So, as I said, the problem is to design a bulk nanocrystalline steel which has a basket of good mechanical properties. It's strong, tough, and it has to be cheap enough to make massive objects. So by massive objects, I mean, for example, this truck, which I photographed in the oil sands mines in Alberta. And if you look at the size of just the wheel, compare with, for example, my size or that of my colleagues, we are talking about very large structures which are large in all three dimensions. Now, what do we mean by nanostructured? We want something that is has a structural scale, a length scale comparable to carbon nanotubes. And what do we mean by cheap? We must be able to produce this material at the same price as bottled water, whether we consider weight or volume, it doesn't matter. Okay? I mean, this has to be one of the most wasteful purchases that anyone can make, because you're collecting water from somewhere, putting it into a bottle made out of plastic and transporting it from its site to all over the country in lorries. Makes no sense at all when you can get perfectly good water out of the tap in most circumstances. Anyway, that's by the way. We're after making steel which is as cheap as bottled water, because bottled water seems to be affordable. Okay, let's think about what nanostructure actually means. Now, if I measure the grain size using a mean linear intercept, then if you recall the lecture on perlite, the amount of surface per unit volume is equal to 2 divided by the mean linear intercept. So this is plotting here the amount of surface per unit volume. And this is in nanometers to the -1. But a value around here corresponds to about 100 million square meters of interface in 1 cubic meter of material. Now, notice that at first, the amount of surface per unit volume doesn't change very rapidly, but around 20 nanometers, it starts to rise sharply. Okay? And this trend is also reflected in mechanical properties. So here, if you look, 20 nanometers is around 0.1 in terms of surface per unit volume here. So if I look at the strength, beyond any grain size smaller than 20 nanometers does lead to an increase in strength, but it's not as sharp an increase as when we go from a large grain size to about 20 nanometers. So let's define our nanostructure as something having a mean linear intercept that is of the order of 20 nanometers. If it is greater than 20 nanometers, then we expect to see sharp decreases in strength levels. Now, we're already here talking about very large numbers. So 2,000 megapascals is 2 gigapascals, and it's hard to grasp the meaning of these very large values of strength. So I'm going to illustrate what that means. Now, an apple has a weight of approximately 1 Newton. A Newton is a force and a weight is a force. So if you put an apple on 1 square meter, then you're experiencing on this square meter a stress of 1 Pascal. Okay? So 1 gigapascal means that this is able to support the weight of 1,000 million apples. Incredible, really. So we sort of glibly talk about strengths of 100 megapascals, 1 gigapascal, 2 gigapascal. But when you think about it, those are incredibly high strengths, and that's what makes steel a very, very useful material. Okay, Now, back in 1956, a strength of the order of 14 gigapascals was already achieved. Okay, and this is in pure iron. So these data come from single crystals of pure iron, and this gives you the size of those single crystals. Now, you can see that there is a dramatic decrease in strength as the size increases. And this is because, you know, if you make your crystal small enough, then it's hard to find defects in it, and defects tend to reduce the strength. So by defects in this context, I mean, for example, dislocations. Once you have enough dislocations in your structure, then the plastic flow stress becomes a lot less than the ideal strength of the crystal, which involves ripping apart layers of atoms. But we are very close here to the ideal strength of iron in tension. We could get to something like 22 gigapascals in tension if we had the perfect crystal of iron and if that crystal of iron was small enough. Now, that's a very important point. When you rely on strength due to perfection, you can only achieve it when the crystal size is small. Okay, so it's a very valuable lesson to learn, that if you rely on perfection, then the strength will drop dramatically because the probability of finding defects increases with the size. I will explain that in a bit more detail later. Now, of course, there is another way of creating a strong steel, and that is by severe deformation. And this is a steel wire with a strength of 5.5 gigapascals, which is available commercially. And you can see that it's extremely ductile, and it also can be tied into a knot. So that is better than, for example, a carbon fiber, which doesn't have this level of ductility. Now, the problem is that in order to get this level of strength, you've got to deform it so severely that there is a very large dislocation density in the material, and the regions which are coherent inside this wire are very small indeed. Now, to get that level of strength, if you imagine that you've got 60 grams of iron and you stretch it out into 2 kilometers, that's the level of deformation that's put into this wire by drawing. So if you look at its atomic structure using a field iron microscope, where every dot represents an atom, and if you squint your eyes, you can see these dark features, and those are dislocation cell boundaries with intense dislocation density, and the coherent regions are reduced dramatically in size. Okay, so we've got to 5.5 gigapascals, which is 5.5 billion apples on 1 square meter. Really astonishing strength. Now, the problem is, okay, so I won't go into the problem just as yet, but if I compare this wire against the single crystal where the strength drops dramatically, this is insensitive to size simply because it acquires its strength not through perfection, but by having lots and lots of dislocations inside the material. The problem is that when you have to put in so much deformation, you end up with an extremely thin wire. And just to illustrate to you how thin that is, if you look at the men's socks or women's stockings, then the definition of that thread is in terms of a denier, where a denier is the weight in grams of 9 kilometers of fiber. And women's stockings tend to be about 10 denier and men's socks about 50 denier. Now, Cypher, the steel wire that I just explained, is 9 denier. So it's finer than the thread in women's stockings. Now, this means that it becomes very expensive, and it cannot also be classified as a bulk material because you can't make large objects with it. You can't weld it either, because that would destroy the structure. Okay, let's move on. Now, this is a carbon nanotube with a particle of iron in it. And when this became a story, there were articles, for example, in Acta Astronautica, where the strength was reported as 130 gigapascals. And of course, that corresponds, to the strength of the carbon-carbon bond. In recent years, people have been talking about graphene being the strongest, but actually you could get a strength of 130 gigapascals in carbon nanotubes. And the reported strength of graphene is of this order, or very close to this number. The reason why this was reported in Acta Astronautica is that the idea was to build a space elevator with a carbon nanotube rope that is, 100,000 kilometers long. And because it would be light compared with any other material that we know, it could support its own weight. Whereas, if you try to make it out of steel, that would not be possible. Okay, and it also has a modulus along its length, which is roughly 6 times that of steel. So that's very good for a rope. Now, if we look at some basic thermodynamics of defects, then this term here, where we have small n, is the number of defects, and this is the cost of creating a defect, then this opposes the formation of a defect. Okay. On the other hand, when you take a perfect crystal and you introduce a defect, that increases the number of ways in which you can arrange the atoms on the lattice, arrange the defect on the lattice, and therefore you increase the entropy, and this is the configurational entropy, and this term will favor the formation of a defect. So if you differentiate this equation with respect to the number of defects and set that to 0, then we get an equilibrium number of defects, and I emphasize the word equilibrium, at any temperature and in any material, right? And that equilibrium number scales with the total number of atoms in your system. So what this means is that once you start scaling up the size of your object, you will have an increasing number of defects in that object. That's what thermodynamics tells you. You can't get rid of them. And this is why we can get diffusion of atoms through a metal, for example, because there are vacancies, and the vacancy concentration, if you set this to the free energy of formation of a vacancy, this represents the concentration of vacancies. Now, this equation tells you immediately why you cannot get the strength levels reported for carbon nanotubes when you make them larger. So if I show you some data here, the strength collapses, okay? Collapses even when you get to a length of 100 micrometers, let alone 100,000 kilometers. And exactly the same principle applies to graphene. It's complete nonsense to talk about the strength of graphene being 200 times stronger than steel. It's only 200 times stronger, as are carbon nanotubes, when the size is incredibly small, okay? Because you are relying on the carbon-carbon bond, not on defects, and defects will be there as soon as you scale it out, okay? And of course, the strength of graphene and of carbon nanotubes is highly anisotropic. So the same reason which we knew in 1956 is that the strength of viscose decreases with size. That should have been a lesson for people working on carbon nanotubes and graphene when they talked nonsense about the strength of the material and what could be made with it. So the strength of a nanotube rope, about 2 millimeters long, is less than 2000 megapascals. So I wrote this up and I sent this article to NASA, who were sponsoring a $17 million project on the space elevator. And you no longer hear about the space elevator being made of carbon nanotubes or anything else for that matter. Actually, the idea for the space elevator comes from Russia, a Russian comic from many, many decades ago. Very imaginative. Yeah, you don't have to launch rockets, you can simply climb up the rope. Okay, so strength produced by deformation limits the shape, and the shape may be in the form of wires or very thin sheets because you have to deform a lot. And strength in small particles relies on perfection and is doomed as size increases. And we've known that for more than half a century, and yet people just do not learn that lesson when they make awful claims about the properties of small samples. Now, there is a process which has been incredibly successful in mass producing steels. It's known as thermomechanical processing, where you have the steel hot deformed in the presence of very small particles of carbides, which limit the growth of the austenite grains, and therefore you can end up with very fine ferrite grains. Okay, so let's see if that process, which definitely is a bulk production process and produces steel samples which are very, very large if you want them to be large, and ask, what is the smallest size that could be produced by thermomechanical processing? This is a grain structure, and I explained to you in an earlier lecture on pearlite that the cost of creating these boundaries here is the surface per unit volume times the interfacial energy, a grain boundary energy in this case. So if I multiply these two, I get 2 sigma over the mean linear intercept as the cost of creating these grain boundaries. And that cost has to come from somewhere, okay? It's provided by the free energy change from austenite to ferrite. So we can calculate the free energy change and set it using thermodynamics and set it equal to this. And then we have a relationship between the smallest possible grain size that can be produced for a given driving force of transformation. In other words, a given undercooling below the equilibrium temperature. So here is the curve showing how the minimum size that could be produced depends on the free energy change. So we would have to undercool to get a size of 0.01 micrometer, which would be very impressive. But it turns out that when a large amount of investment to look at this problem never managed to produce a ferrite grain size smaller than 1 micrometer. Okay? Now, the reason for this is that when we undercool, the enthalpy change of transformation also increases. And furthermore, the rates of reactions can sometimes increase. So the heat of transformation basically removes the undercooling. It heats up the steel. And when we take account of that, it isn't very likely that we can produce nanostructured steels using the hot deformation method. This enthalpy release is known as recalescence. It heats up your material simply from the enthalpy change of transformation. So in summary, thermomechanical processing is limited by this recalescence, the release of the enthalpy of transformation. So we need to do something to help. We need some mechanism of storing the heat inside the material, okay? And think about it, when we were talking about displacive transformations, the amount of stored energy due to the shape deformation in the case of martensite was 700 joules per mole, which is very large. If I go back to the previous slide here, you can see that's a large amount of energy you would consume in creating the elastic strains around martensite. Okay, we could also reduce the rate of transformation to allow any enthalpy to dissipate. And transforming at a low temperature is always a good thing because it increases increases the nucleation rate. I mean, that's an exaggerated statement because if you go too low, you might actually decrease the nucleation rate. But generally speaking, you will get finer structures when you transform at a lower temperature. There's one more problem. Okay, so these are experiments reported on interstitial free iron, where if you look at a grain size of 2 micrometers, we have a strength level there, but lots and lots of elongation. But if you decrease the grain size by an order of magnitude, it's not nanostructure, that is small, you get a rapid plastic instability. So there's almost no uniform elongation. Now, the reason for this is when you make the grain size small, the defects sink into the grain boundaries. Once that happens, there's no work hardening mechanism, and therefore you get rapid plastic instability. Here, when the grain is large, you have the dislocations moving about inside the grains, and therefore you delay your plastic instability by work hardening. But at fine grain sizes, you lose that ability, and therefore you get an early plastic instability. So the fourth condition is that we must have a mechanism of introducing a work hardening capacity. Now, at this point in the lecture, I ask the students, how would you increase the work hardening capacity? Because we've done it already. We've done it with the trip steels, for example, where a small amount of retained austenite in the microstructures transforms at stress concentrations and gives work hardening, and therefore we get a large elongation in spite of an increase in strength. Okay, so in summary, if we choose a displacive transformation, then it would have to be bainite because we are talking about the ability to produce large samples, which you cannot quench without, cannot uniformly quench without adding huge quantities of alloying additions. And we need to avoid distortion associated with rapid heat treatment. Okay, and the work hardening capacity, if we choose bainite, would come in from the retained austenite if we add silicon to our alloy. So this is the shape deformation due to the bainite transformation, and it introduces a stored energy term of the order of 400 joules per mole, which is quite large. And as I said to you, we will cut the reaction off at this point so that we end up with a mixture of carbon-enriched austenite and bainitic ferrite plates. And I showed you this microstructure, which is beautiful with these fine platelets of bainite and bainitic ferrite and retained austenite in between. But this is not a nanostructure. It's about, each of these plates about 1/4 of a micrometer in size, and it's transformed at around 400 degrees centigrade. So we need to suppress that transformation temperature. So you can ask a fundamental question, what is the lowest temperature at which I can get bainite? Okay. And we can do those calculations. I haven't explained to you how to do that, but I explained to you how to do the Martin's start temperature calculation using thermodynamics, etc. And we have the theory for the bainite reaction. And when we apply the theory, it's actually quite surprising that as long as you can keep the bainite and the Martin's start temperatures separated, okay, you can suppress the bainite start temperature to room temperature. Okay, so you can actually form bainite at room temperature in this alloy and this sort of carbon concentration. Very surprising, okay? But there is nothing to say that this is wrong. There is a spanner in the works, and that is that the kinetics of reaction becomes slower as you suppress the transformation temperature. That is good as far as the dissipation of heat is concerned. But at this carbon concentration here, it would take a century for bainite to form. So you could make the steel and leave it for a century, just like wine in a cellar, and it would appreciate in value, and later on you might be able to sell it. But unfortunately, we don't have that patience. So we make an alloy which will transform in about 10 days, okay, of isothermal heat treatment and at about 200 degrees centigrade. So we've achieved the low transformation temperature by having a carbon concentration of 1 weight percent. This is to suppress the cementite, hardenability. We want to make large quantities of this material, so it will inevitably contain impurities which segregate to the austenite grain boundaries, for example, phosphorus. And we do not want that because strong steels become brittle at the boundaries if there are impurities. And the addition of molybdenum cures that problem by gettering the phosphorus. And this is again a hardenability addition. Now, it's a fairly simple alloy, and we've got enough hardenability to avoid pearlite and ferrite in a large chunk of material. Reasonable transformation time. So 10 days at 200 degrees centigrade is perfectly reasonable. It's like putting the steel into a pizza oven. It's not expensive. And we've got rid of cementite. Vanadium is there to form small vanadium carbides, which help to control the austenite grain size and stop it from coarsening, and molybdenum to avoid the embrittlement. The heat treatment is straightforward, that you austenize and then you hold at 200 degrees centigrade for 10 days. There's no need to quench it afterwards. You can cool it slowly. So we did this, and we obtained a structure which looks like this optically. Okay? So this is bainite, and the white regions are austenite, and there are films of austenite between the platelets of bainite, which you cannot see. So on its own, this doesn't look remarkable, but I want you to note that this structure is effectively isotropic, because I'm going to show you a very high magnification image of one of these regions, which can be completely misleading. So this is the breathtaking transmission electron microscope image showing the platelets of bainite and the carbon-enriched retained austenite. And this scale here is 20 nanometers. So these are approximately 20 nanometers wide, finer than this carbon nanotube at the same magnification. It's remarkable, actually. Now, you may argue that, okay, these are long, but the mean free slip distance in a plate is twice the thickness. If you do a stereological analysis for the mean free slip distance, because slip in the plane of the plate is very unlikely, then it's twice the thickness. So we've achieved an incredibly fine grain size purely by phase transformation, which has an isotropic structure, and there's no rapid cooling involved in this process, so you don't have the distortion. And sure enough, you get work hardening, and depending on your transformation temperature, you can control the strength. This is about 2 gigapascals and about 25%, let's say 22% elongation. Now, the temperature of transformation is a quarter of the homologous temperature. That means the absolute temperature divided by the absolute melting temperature. So it's a remarkably low melting temperature, heat treatment temperature. And what this means is that the diffusion distance of an iron atom in 10 days at 200 degrees centigrade is unphysical. It's 10 to the minus 17 meters if you calculate it. This can only happen, this transformation can only happen by a displacive mechanism. That's obvious, okay? And we have achieved an incredibly fine structure, finer or comparable to a carbon nanotube. And this is actually very hard because we have 100 million square meters of bayonitic ferrite austenite interfaces inside our structure. And those are strong interfaces because a dislocation would have to traverse into a different lattice, different crystal structure. There are no carbides and designed using nice, neat theory. Okay, so the properties are impressive. And in the Cavendish laboratory, they did very high strain rate experiments. And you can see that so this is a projectile being fired at the nanostructure steel we have developed. And elastic deformation ceases around here. So the material can support this high velocity impact elastically up to 10 gigapascals. And this is the mass production of the material. Now, of course, these coils are not the nanostructured bainite because you would not be able to uncoil them. It's so strong. So they're produced in the pearlitic condition, and then it will be sliced up and heat treated to obtain the right structure for the components. And this is, an armor test. But this is the really interesting thing, that ballistic mass efficiency is, the mass of ordinary armor to defeat a given threat divided by the mass of the test material to defeat the same threat. And super bainite this nanostructured bainite outperforms normal armor, the titanium alloys. So we are taking account of mass, don't forget. And alumina, which cannot take many shots because it's a ceramic. On the other hand, this armor can take many hits without allowing them through or fragmenting them. These holes here are designed as edges which would tend either to deflect the projectile or to fragment it. Now, another potential application is in aero engine shafts. This is a picture I took many years ago at Heathrow Airport. And you can see the size of this engine compared with the lorry. And the newer engines are even wider. And the reason is that, a lot of the air actually doesn't go through the engine, but it provides thrust as these fan blades rotate. And there are advantages to that sort of a mechanism. So here is the structure of a civil aircraft engine. And this is the steel shaft that transmits the torque to the fan blades. Now, we would like to make this out of nanostructured bainite, and these are actually blanks of nanostructured bainite for prototype shafts by Rolls-Royce. Okay, so just think, these are very large. The diameter there is about 150 millimeters or so, and the heat treatment is, you austenize it first, you remove them from the austenizing furnace and put them into a salt bath at the appropriate temperature. Okay, this is the salt bath at 200 degrees centigrade, but you don't want to leave it in there for 10 days because this is expensive kit. So you take it out and you put it into an oven at 200 degrees centigrade. Okay, so here is two of these shafts heat treated, and they have this structure throughout, uniform hardness through the section. So this is very strong. It has a significant uniform ductility. I showed you some tensile properties. We do not require deformation to produce this structure. There's no rapid cooling necessary, so you avoid problems of distortion, and no residual stresses built in from the cooling process. And you saw the chemical composition is not particularly expensive, and we can get uniform properties. Now, there is another application, which is also an important application. So this is a very large bearing for wind turbines. And the rolling elements that you see here, yeah, they are made out of the nanostructured bainite. Obviously, there are many variants today of the nanostructured bainite. So it isn't the composition that I showed you earlier, but this is an actual bearing with the nanostructured bainite rolling elements. Now, at the moment, the factory concerned doesn't have a facility to make such large rings using the heat treatment required, but they can make smaller rings, bearing rings, by the same concept. And that is work in progress. Okay, I want to finish off by telling you some disadvantages of nanostructured bainite. I've talked about shafts, about bearings, about armor. None of those require welding. If you try to weld this, it will crack spontaneously in front of your eyes because we have about 1 weight% of carbon. Okay, so applications are limited to scenarios where you do not need to join the material. There's another story I can tell you in the future of how to solve this problem and yet get this properties the same as the nanostructured bainite. But that's another story. Now, I mentioned to you that if you have this sort of a carbon concentration, then it's going to take 100 years to produce bainite. But we nevertheless made this material. Okay, so this material has 1.75 weight% carbon, and the similar manganese and silicon concentrations, and it looks like this. And it ought to transform at room temperature in 100 years. Now, this experiment was started in 2004, and a sample polished, metallographically polished but not etched sample was produced and put inside an inert gas in a sealed silica tube. And there were 2 of these samples. One is located in the Science Museum in London. And in the year 2104, it will be interesting to see if there is the surface displacements produced by the formation of this bainite. Now, unless the biologists do something miraculous, I won't be around to see this result, okay? But I expect you and your children and your grandchildren to have a peek at the Science Museum in the future. So pass on this story. Okay, that's the end of this lecture and indeed the end of this lecture course. Thank you.